Well, I think we can start. So today we'll talk about. We'll start with the first calculations of scattering in quantum field theory. Specifically now we'll start with things which we already know. So we will start with processes that can be also described classically and non-relativistically. Specifically, the Yukawa potential between scalars, the Coulomb potential between electrically charged particles, and Rutherford scattering, which, well, can be treated as a quantum mechanical process, but there's also a classical scattering related to it. So we'll start with the Yukawa potential. And we'll start with it just because it's the simplest. The interaction between two scalars is the simplest thing we can think of, even though perhaps it's not so fundamental as the Coulomb potential. The Coulomb potential is actually something that is not an approximation. It's an exact. It's an actual interaction between fundamental particles. The Yukawa potential, on the other hand, has been introduced to describe nuclear physics, and it's an approximation in the case that we can ignore QCD, so ignore magnitude physics, and only concentrate on low energy interactions. Low energies, the interactions of QCD are mediated by pions, which are scalar particles. And then we can treat interactions in this way. But in the theory put forward by Yukawa, we don't distinguish between fundamental and composite gauge force particles, and what we're really interested in is the interaction between two fermions mediated by a scalar. So we'll have two fermions, one with momentum p, one with momentum k, and these will scatter into the same two fermions, one momentum p prime, one momentum k prime. Remember, I said this is classical and non-relativistic. So that's why, the particles cannot change, they have to remain the same. And then if we want to write final diagrams corresponding to this, if we put time going up in the diagram, I mean, the conventions depend, but for the moment I'll just use this one. So the first fermion, let's say, has momentum p, and the second fermion has momentum k. And then they have to pass by unchanged, so only the momentum is supposed to change. So this one turns into the same fermion with momentum p prime, this one with momentum k prime. Right? And then the simplest thing that can happen is indeed to have this exchange of a force particle. Now, specifically, I want this to be a scalar, and then I'll denote it in the context of this diagram with a dotted line. So here we'll have momentum q being exchanged. And of course, the classical interpretation is that this fermion emits momentum q and it's recoiled, and then this one absorbs momentum q and it's recoiled. So that's clearly an interaction that can be described classically as a potential interaction between two particles. Now, in principle, so this would be a scalar phi with some mass and phi being exchanged. Now, in principle, if we cannot distinguish between the fermions, if there's no way to say which is which, so that would correspond to something that is clearly not classical. Classically, we can always distinguish the particles. But if we would think that we cannot distinguish the two particles, then we could also have the diagram where the roles of the two fermions are exchanged. So I could write the same thing, the same thing here. But for momentum p prime, measuring as if it comes from this, it actually comes from this. And k prime from this, right? So this would be for indistinguishable fermion. But we'll not consider this here, because we're interested in really the classical Galois potential. And classically, as I said, we can always distinguish them. And quantum mechanically, we can say, well, maybe we prepare these things in different spin states, and we can measure the spin, or something like that. Or even more radically, I mean, I didn't say what kind of fermions these are, but another possibility would be, let's say this is an electron, this is a muon. So then clearly we can measure which is which, because they have different masses. Okay. Anyway, in our setup to calculate the classical potential, we'll ignore the second diagram, assume that somehow we can distinguish the fermions.
Professor?
Yeah.
Excuse me, in which sense this process is classical? Because do we have a clear notion of fermions in classical physics?
No, not of, well, we don't have a notion of a fermion field. We certainly have a notion of a fermion. We know what an electron is, right?
Yeah, right.
We can measure an electron. We can, make a beam of electron, make it shoot on some.
But another thing is that the exchanging particle requirement or idea is spiritual. So how can this be classified as spiritual?
Well, yes, but so as long as these particles are not created or destroyed, then the particle itself is classical, and the fact that it exchanges a virtual particle is what replaces in quantum mechanics the classical process, right? The classical process says, well, there's some instantaneous interaction between the two particles. But in quantum mechanics, we say, well, wait a minute, it's not instantaneous. Well, we're non-relativistic, so it looks almost instantaneous, but the point is that it's due to the exchange of a particle, right? So in order for it to be classical, the only thing we have to say is that the particles are not created and destroyed. The process is non-relativistic, right? So that we don't need to deal with quantum field theory, the full quantum field theory, right? And well, that we're not interested in other things like, the particle is still quantum mechanical particle, so it has errors in position and momentum and so on. We're not interested in that. We're just interested in the force between them, which can be detected by, say, the scattering potential, the Rutherford scattering that we'll get to, Rutherford type scattering. Then That's the equivalent in quantum mechanics. Okay? All right. And then I said we also want the non-relativistic limit. So in the non-relativistic limit, we'll assume non-relativistic limit means the momentum is much smaller than the mass, which means that the energy is approximately equal to the mass. So P is mP, and K is mK. So here I'll assume all the masses are equal, which is, well, not necessarily true, but also will not change anything at this point. Okay, and then we note in here that Q must be equal to P minus P prime, right, from momentum conservation at this, or it's also K minus K prime from momentum conservation. Yeah, also K minus K prime from momentum conservation at this vertex. So the thing that appears in the Feynman diagram is this Q squared, which is P minus P prime squared. And then the energy is approximately 0, so then this is approximately equal to P minus K, P minus P prime squared. And finally, the last thing that I need, these are fermions that come with an US. So a fermion will come with an US of P, fermion of momentum P. And in this case, it's non-relativistic, so the normalization we'll have is square root m. And then you remember this comes with 2 copies of psi s. And then psi s is this 1, 0 or 0, 1, or is 1 or 2. So then also means that if I have the combination u bar of s prime, u bar s prime of p prime u s of p, this would be u dagger I gamma 0, dagger s prime I gamma 0 u s, and substituting this, we'll get 2 square roots m, so that's an m. Then psi s prime, I gamma 0 was 1, 1 on the second diagonal. And here, again, psi s. Well, I guess psi dagger should be, really, meaning I put them horizontally instead of vertically. And this is what? So this is second diagonal, so it connects psi dagger s prime with psi s. And the same for the other one, so you get 2 terms, 2 equal terms, 2m psi dagger s prime psi s. And of course, psi s being this 1, 0, 0, 1, this product is delta s prime. If s is equal to s prime, this is just 1, 0 times 1, 0, which is 1, and if not, it's 0. So this is 2m delta s prime, right? Okay. So then, in in IN, I would write so let's write consistency. So a trick is when you write fermions, you think about going opposite to the fermion line. So I start with U bar, I go opposite on this line, so it's U bar of P prime, then U of P, right? Then I will have the propagator in here, and here the same thing, U bar of K prime, U of K. So minus Ig from the vertex. The vertex here is G. So I have minus Ig from the first vertex, then U bar of P prime, U of P. Then the propagator, which is minus I over Q squared, which is P minus P prime squared plus the mass squared. Then another vertex minus Ig, and another U bar K prime, U of K. Okay. And more precisely, this would come with indices, so this would be S prime S. And, well, here let's call them R prime and R, right? So, for completeness, just to get, because part of the reason to do this is to get a handle on how to write Feynman diagrams. Let's also write the second Feynman diagram. And then, well, I would have also minus Ig. And then, remember, we're always going against the arrow in a fermion line. So I would write U bar K prime U of P. Then minus I over P minus K prime squared plus M phi squared. And then minus Ig U bar of P prime U of K. But then if we use this convention, then we will have a minus sign for the second diagram relative to the first. Now, the sign in a diagram involving fermions is somewhat conventional. What's not conventional is the relative sign. So let's see in this more precisely. So if I have a state corresponding to fermions with momenta P and K, that amounts to having a dagger P, a dagger K acting on the vacuum. And then, so this was an initial state, and then the final state has the fermions of momentum P prime and K prime. So that's a bra momentum K prime, P prime and K prime. So this is the dagger of this, right? So this would mean well, 0, A K, A P, right? P prime, K prime and P prime. So So the matrix element that we will have in here, remember for S matrices we have contractions with external states. So the matrix element will be P prime, K prime, PK. And here we will have two interactions that are of the Yukawa type that we've described already. So it's the type psi bar psi phi, right? This vertex. The phi doesn't interest us. That's, well, I mean, that will just give the propagator, but now we're talking about the fermions. So there will be a psi bar psi if I call this point vertex x and this vertex y. It's a psi bar psi at x and a psi bar psi at y. Right? So let's say I do the contraction like this. All right. So, well, first of all, this was, as we said, this was 0 AK AP. And this was A dagger P, A dagger K, 0. Okay, so psi bar psi y, psi bar psi x. So doing the contraction this way. K prime is psi x. K prime psi bar x. All right, so this would be the, let's say this would be the first diagram. In the sense that I have, well, yeah, so.
Should you connect one of the x with one initial state and with one final state? You connect two operators on x with the two final states.
Well, yeah, I mean, what I'm saying is, what does this diagram mean? So we're having this vertex. We're having this vertex, and these are external lines. So what I'm doing, this is x. I'm connecting this with this. This is the external line, the A dagger. And this is the vertex, psi bar psi. And I'm connecting this
you're
and
connecting
this.
one initial state to one final state, right? The time is upwards. So for me, it seems like you're connecting the two operators that are evaluated on x to the two final states. To one final and one initial state.
No, sorry. Yes, you're right. Yes, you're right. You're right. Yeah. So let's see. So I'm connecting. I want to connect. Let's say P prime with. P prime with psi bar y, and then psi y with P, then K prime with psi bar x, and like this, right? I think that's.
Just interchange x and y in the
And then I say k prime with psi bar x and p prime with psi bar y, and then psi with k, psi y, right? Okay. All right. So then this is the first diagram, and let's see how many signs we have in this. So all of these things now are fermions, right? So switching them gives a minus sign. All right, so this is no minus sign. Then this one, to get in front of this, has to go past 1, 2, 3. So there's a minus sign. Then this is gone. Then this one has to go past 1. So another minus sign. And then this one has to go past 2. So there's, no, well, a plus sign. So all in all, this is plus, right? Now, if I would, now doing the same thing for the second diagram, like k prime, psi bar psi at x, psi bar psi, psi bar psi at y. Well, let me just write it already like this: 0, a k prime, a p prime, and a dagger p, a dagger k, 0. And now I want to switch. So I want to contract p prime with k. So let's say p prime, and here with k, and then k prime with p. Okay, so now let's see how many signs we have. So this one contracted with this one, so going past 1, that's a minus sign. Then this one connected to this one. Now this is gone, there's only one, just another minus sign. Then this one, with this one, there's one left, so another minus sign. And then this one, there's nothing left, so there's a plus. So all in all, I have minus. Okay? So, so as you see, with this convention, writing the states like this, the first diagram has indeed plus sign. But then the second diagram, and as I said, this plus sign is kind of conventional, so the overall sign of the amplitude is conventional. And it doesn't matter because in the final amplitude you have the square in the S matrix. So that's unobservable. But the relative sign is important. The relative sign in this case is definitely minus, as I've written in here. And remember the Feynman rule that we used last time. I put as a Feynman rule, and I said, well, if you're careful, you don't need it. Being careful means writing what I just did, remembering that these are contractions with external lines and doing all of them carefully. But the simple form is to say, if I switch to fermions, I get the minus sign. That's what I did here. I switched to fermions, I got the minus sign. External fermions, right? And then the point is that you don't need this convention. You don't need to know the actual sign of the first diagram. The only thing you need to know is the relative sign. And then the only thing you need is this final rule that switching the external fermions gives a minus sign. All right. Okay, so I put this second diagram in here just to emphasize this important point about fermions, how to deal with signs. But we're doing now the non-relativistic classical process, Yukawa potential. So you can forget the second diagram, and we just have the first diagram. And then let's say we get that Im is equal to, we've just seen that U bar is prime of B prime US of P is 2m delta SS prime. So this is 2m delta SS prime. And similarly, this second term is 2m delta RR prime. So Im is then minus ig squared, which gives minus g squared, with minus I, so ig squared. Divided by p minus p prime squared is just the vector part, so p vector minus p vector prime squared plus m phi squared. And then I have these factors, 4m squared, delta SS prime, delta R prime. Okay? So that's the value of the matrix element. Okay, so now how do we get from this to the potential? Well, you remember the potential is not something measurable per se. We measure it indirectly, meaning that what we really would compare would be the scattering in a classical potential versus the scattering using this quantum mechanical amplitude, right? But as a shortcut, what we do is we compare with the Born approximation for the scattering in non-relativistic quantum mechanics. So standard quantum mechanics, non-relativistic quantum mechanics, which is that this amplitude is given just by minus I, the potential as a, Fourier transform in momentum space as a function of momentum q, which is just the difference between p and p prime, times 2 pi delta ep prime minus ep, right? So, yeah, so this is what we're doing now as a shortcut. But there's one more thing to remember. So this is non-relativistic quantum mechanics, standard quantum mechanics, scattering and standard quantum mechanics. But these factors of 4m squared here came from this, and well, rather I should say came from this condition, right? So this condition was a normalization for the fermions, but the normalization that we used was a non-relativistic one, a relativistic one. So this came from normalization, but this is relativistic normalization. All right? But then this relation is non-relativistic in non-relativistic quantum mechanics. So I have to drop these factors in the comparison with this. simply because this was used assuming a non-relativistic normalization. Okay.
To write this square root m that you subline there, have
Yeah.
to take the non-relativistic limit?
Non-relativistic limit, but the point is the normalization itself, right? The normalization itself was relativistic.
Yeah.
Yeah, I mean, m is non-relativistic, it's a mass, right?
Yeah.
I don't mean that. What I mean is that this came from a normalization of the external states, which was relativistic, whereas this formula assumes a normalization that doesn't know. I mean, m, you know, m is the energy, the relativistic energy at zero momentum, right? But non-relativistic, there's no m, there's no energy, right? All right, so and then then I also remember that this IT is In times 2 pi delta. So this 2 pi delta is also cancelled when I compare the two. So all in all, I get that V of Q is minus G squared over P minus P prime squared plus M phi squared. Okay. So this is this is a shortcut. I mean, if I wanted to be a little bit more rigorous, but there's no point really, I would have compared d sigma d omega in both ways, and then just compare the results and try to figure out what the potential was. But there's really no point. This is enough, and by doing this, we know that we'll get the correct scattering. All right. And now, of course, you know, we're not used to the momentum, to the potential in momentum space, so we need to consider the potential in coordinate space, which is just a Fourier transform. So integral d3 q 2 pi cubed e to the I qx times this minus g squared over p minus p, q squared plus m phi squared. Right? So let's put constants out front. And then this integral also, right, it has 2 pi integral over angles. Maybe let's be more careful. So I say q squared dq times d phi sin theta d theta, right? And then this is e to the iqx cos theta. The integral over d phi gives 2 pi. This is minus d cos theta, but then the integral will be from 0 to pi. So this is equal to integral from, now I switch, cos 0 is 1, cos pi is minus 1, but I switch the orders of the integral and I cancel therefore the minus. So I get integral from minus 1 to 1. So I get 2 pi and the integral from minus 1 to 1. D of this cos theta eqx cos theta, right? And this is what? This is integral 1 over iqx, right? Times e to the iqx times cos theta at the maximum, which is 1, minus the same thing at minus also, e to the minus iqx, okay? All right, so this is minus g squared over 2 pi cubed times 2 pi integral q squared dq e to the I qx minus e to the minus I, well, I guess I called it r. Yeah, maybe let's call it r. Minus IQR over IQR, and then 1 over q squared plus n phi squared. Okay? This is from 0 to infinity. All right? But now, I note that these two terms are, so this is what would happen if I would have an integral from minus infinity to plus infinity. So if I have, instead of, so the first term is just the integral from 0 to plus infinity. The second term, the minus sign, I can use it, the minus sign I can use it to switch the integral, the order of the integral, instead of being from instead of being from 0 to infinity is from infinity to 0. So the minus sign is switched to be an integral from infinity to 0. But then I change the sign of q, so q going to minus q, and then this is integral from minus infinity to 0, and then I get rid of this minus sign in here, right? So all in all, I get the integral from minus infinity to plus infinity, right? And 1q cancels, so I have dq, then 1 over ir outside, e to the iqr, 1q remains, and then q squared plus n phi squared. Okay? So we get that v of x is actually v of r, and is equal to minus g squared over 2 pi cubed times 2 pi from here, then 1 over ir. And then integral minus infinity to plus infinity dq q e to the iqr over q squared plus n phi squared. Okay? And in order to do this integral, I use integration of a contour. So I turn this into an integral over the complex plane in Q. And then I note that this function has poles at Q equal to plus or minus I and phi. So these poles at Q equal to plus or minus I and phi, when Q squared plus n phi squared is 0. So the poles would be here and here, I and phi. Minus I and phi. And the integral is over the real line, right? Let's remember how we do these things. We consider an integral over a semicircle at infinity, and we choose the semicircle either in the upper half plane or in the lower half plane, such as the integral to be 0. And I have this factor e to the iqr in here, which means if q has negative, if q has positive imaginary part, then this would be I squared, which is minus 1. So it would be minus imaginary part of q times r. And if imaginary part of q goes to infinity, then this vanishes. Okay? So choosing the contour in the upper half plane, choosing this contour in the upper half plane does nothing. The integral of this is 0 because of this exponential. But now this is the integral over the contour, and the integral of the contour is equal to the residue at the pole. The pole is at I and phi. Okay? So this is 2 pi I times the residue at the pole. So 2 pi I times, let me write it here. U of r is equal to, well, minus g squared over 4 pi squared, 1 over I r, that is in front. Then 2 pi I, then the residue of that function. So q is equal to I and phi. Then e to the I qr is e to the I times I and phi over r, so minus n phi r. And here is the residue, so this would be q plus I and phi times q minus I and phi, but I have to get rid of q minus I and phi. And then q plus I and phi is 2 I and phi, right? 2 I and phi. All right, let's see if I got the right result. So minus g squared over 4 pi e minus I and phi r over r. Yeah. Okay? All right, so this is the potential in X space. And we note what? Well, it's 1 over r, right? So first of all, this is the Yukawa potential, but let's be more precise. So it's 1 over r. That's clear. It has this exponential, so it's has finite range of the order of 1 over n phi. And it has a minus sign, it's a negative potential, so that's attractive. Okay? So that's what we knew about the Coulomb potential. About the Yukawa potential. And now let's do the same for the Coulomb potential. Okay, Coulomb potential means the interaction due to electromagnetism between the same objects, let's say fermions in this case. So IM in this case is this. So this is actual QED. So what we had before was, in this low energy theory for QCD, which is nucleons interacting with pions. Nucleons are fermions, the pions are scalars. Force particles between nucleons are scalars. But the real fundamental interaction is for the case of the Coulomb potential, where we have the interaction of the fermions by an exchange of a massless photon. Before we have this thing, okay? And then we get what? So IM is, well, the vertex in here is, as we saw, plus E. Right, so with respect to the previous case, we have another I, so minus I times I gives plus. And then the same thing, so U bar S of P prime, but now with the vertex has also a gamma mu, right? So gamma mu and US prime, US of P. Now, the propagator for the photon is just g mu times the scalar propagator for a massless scalar. So minus I g mu over, well, Q, but in this case is P minus P prime squared. And then the same factor on the right, so I have plus E, U bar R prime of K prime, gamma nu, U R of K. All right?
Where is the second term on the propagator for photon? The alpha term? 1 minus alpha?
No, yeah, this is in the Feynman gauge, right? I mean, okay, the physical things like S matrices for scattering will not depend on gauge. Individual Feynman diagrams will depend on gauge, so there will be an alpha dependence. But since, we want to compare this with this non-relativistic story. So, in principle, as I said, the correct thing to do would be to just calculate d sigma d omega, which is gauge independent, and then measure against what we get from non-relativistic quantum mechanics and try to figure out what the potential is. That would be, let's say, rigorous result. But we want to do this shortcut, and then, we choose the simplest gauge that does what we want, and that's the Feynman gauge. Otherwise, you're right. If I put here something that depends on alpha, then obviously the amplitude itself will depend on alpha. And that's not surprising. So, amplitudes in gauge theories, individual Feynman diagrams in gauge theories depend on the gauge. Anyway, so
how will this individual Feynman diagram depend on this gauge, on this alpha? Actually, not exactly a gauge. But at the end, you will have a scattering matrix. You said that wouldn't depend on it.
Yeah, I mean,
you have to choose one value of.
No, obviously it cannot depend on gauge. It's a physical thing, right? And the point is that the remnant of the gauge invariance in amplitudes is given by these word identities, or in the case of QED, word Takahashi identities. Right? And so the word Takahashi identities apply to all the amplitudes. And then the implication of this word Takahashi identities is really that there's no gauge dependence. So it's a statement of gauge independence. And therefore, by using them, you should be, by using them, which are relations between amplitudes, you can show that the final result for d sigma d omega, which is in terms of n squared, is independent.
So those are the entities end up choosing the value of.
No. Though choosing that there is no preferred value of alpha, showing that there is no preferred value of alpha. It's gauge independence, alpha independence. Okay. So we're interested in the non-relativistic case, as we said. We just want to compare with non-relativistic theory. And then we can check that the only non-zero components are mu equal to 0. So, well, first of all, first of all, G mu nu makes mu equal to mu, but then you can do this calculation. You can do it yourself and verify that the only non-trivial components in the non-relativistic limit are the mu equal 0 ones. And that's kind of expected because, well, that's what happens in the non-relativistic limit of anything, right? Just if you have a vector, only the mu equal to 0 component contributes. So then in the non-relativistic limit, so in the non-relativistic limit, then we have this object, u bar s prime p prime. Well, we could even say u dagger times I gamma 0. And then from here, I also have gamma 0. So gamma 0 squared and us of p. And gamma 0 squared is minus 1, right? We have gamma nu is 2 g mu nu. Means that 2 gamma 0 squared, for mu equal nu equals 0, is 2 times metric, which is minus. Right? So gamma 0 squared is minus 1. So this is equal to minus I, then u dagger s prime p prime us of p, right? But then we said that this is psi s, and this is psi dagger s prime, psi dagger s prime, with the square root 2m as a common factor. So all in all, with a square root m. So all in all m, and then these give a 2 times delta ss prime. So all in all, we get minus 2mi delta ss prime. All right. So then this thing gives minus 2m delta ss prime, if you want delta times delta mu 0. And then this one minus 2mi delta r prime delta nu 0. Maybe it is here. So we get that Im is equal to, well, let's see the minus and I. So we have minus I, minus I, minus I. So that gives minus I cubed, which is plus I, right? Then E squared, so I E squared. Then G00, 0, and then what? 2n squared delta ss prime delta rr prime over p minus p prime squared, right? And G00 is of course equal to minus 1. And so cancel the I. So already we can see we don't need to make any more calculations, so we just compare with what we had before. So before we had m was equal to ig squared over p minus p prime squared plus m phi squared times 2m squared delta ss prime delta rr prime, right? This was in the case of, sorry, without that. So this was for the Yukawa potential. I put my all right. So we can see already what happens. So it's the same result with just G replaced with E. There's an extra minus sign, and M phi is equal to 0, right? So we can already write what the potential is. So V of R is just now, instead of being attractive, instead of having minus sign, now it's repulsive, has a plus sign. So plus E squared over 4 pi R. There's no exponential because M phi is now replaced by 0. Okay, so we just get the Coulomb potential, E squared over 4 pi being equal alpha. Okay, and as you know, this E squared over 4 pi is approximately 1 over 137. So it's very small. All right. All right, so we've calculated two relevant potentials, the Yukawa one between fermions exchange that the potential due to a scalar of mass m, and the Coulomb potential due to photon exchange. Now, these were, however, only for particles of the same type. So we've considered fermions that had the same arrows on them, which means that they're both either fermions, so particle and particle, or both antifermions, so antiparticle, antiparticle. But now let's consider what happens also for particle-antiparticle scattering. And I suppose I should have left somewhere the formula I had before. So maybe let me write it here again. So Im in the case of Yukawa was equal to minus Ig U by S prime of P prime US of P minus I over P minus P prime squared plus M phi squared minus Ig U bar R prime of K prime U R of K. And now let's consider the scattering involving particles and antiparticles. Okay. So, as I said, now we consider the case that the arrows point in different directions. Let's say this is a particle, time goes up, and this is an antiparticle. And the first case we'll consider is Yukawa. So this is P prime, but then this is K prime. All right. So what does change? Well, remember that we're contracting each individual fermion line, and in the direction opposite to the arrow. So in the case of the first line, nothing changes. The first line is the same. The only change is here, right? So here now we have to go in the direction opposite the fermion line, and also before these were U's corresponding to particles. Now these are V's corresponding to antiparticles. So going in the opposite direction, we have V bar S of K. So what we're replacing is, we're replacing U bar S prime of K prime US of K, which was what we had before. We're replacing that with V bar of K, S of K, V S prime of K prime. Okay? And the difference is that, as you remember, Vs of K is psi s and minus psi s. So this is V dagger times I gamma 0, and I gamma 0 is the same off diagonal 1. But now this is psi dagger S, psi dagger S, but with minus 0, 1, 1, 0 times psi S prime minus psi S prime. Okay? So this one from before was 2m delta SS prime, right? Whereas this one is what? So in here I contract with this, I get minus psi S prime, contracting with the first, plus psi dagger S. So minus square root m delta SS prime. And the second, psi S prime, contracted minus psi S. So again, the same thing. So minus, minus 2m delta SS prime. Right? So we see that with respect to the first one, the only thing that changes is an extra sign. All right. So with respect to this case, I'll get an extra sign, but if you remember, this was compared directly to the potential. So that means that the potential between particle and antiparticle is equal to the opposite one, so plus g squared over 4 pi r e minus n phi r. Okay. Oh, no, sorry. Yeah, this doesn't. Where's the second sign? No, but sorry. Yeah. So the other sign that comes into play is because I can think of exchanging fermions to the fermion line to an antifermion line is the same as just exchanging these two external lines, right? So if I exchange, so initially I had so in the first diagram, in the fermion diagram, I had K and K prime. And now if I exchange these two lines, this line will point downwards and this line will point also downwards. So I will get the fermion-antifermion exchange. And another way of seeing that is, of course, directly through the contractions. So now I have, for this contraction, I have a dagger, a wait, so this first one was a dagger K, P, and then psi, a dagger K prime, P prime, psi bar psi X, psi bar psi Y, sorry, A, then a dagger K, a dagger P, a dagger K, 0. And so before we had the contraction of K prime with K prime with psi bar, and psi with K. And now yeah, now I basically substitute these things, right? I basically switch the contractions of psi and psi bar in order to get in order to get so I'll get V of k, V bar of k prime. And which amounts to the new yeah, I mean, it's basically this. We have to exchange this psi bar with psi inside the vertex, and that gives an extra minus sign besides the one that comes from the Lorentz invariance contraction. I mean, yeah. All right, so there's a minus sign from exchanging the external lines, which is the same rule as when we exchange these two external lines. Also exchanging these two external lines, so final with a final with an initial external line also gives a minus sign. The way I tried to show here, I was a little bit confused, but it's the same rule. So you get an extra sign. But then the contraction itself of the V's gets a minus sign with respect to the contraction of the U's. So all in all, we get plus sign, which amounts to the potential being, again, attractive. So the scalar exchange is actually universally attractive. On the other hand, maybe I'll leave this here. On the other hand, for the Coulomb case, for the same diagram with an exchange of a photon, so here having mu, here having nu, the same change happens, but now we have u bar s prime gamma 0 u s of k being replaced by v bar s of k gamma 0 v s prime of k prime. And this was equal to u dagger s prime I times gamma 0 squared, which is minus 1 times us of k, which was equal to minus 2mi minus 2mi delta ss prime. And this is replaced with v dagger s of k gamma 0 vs prime of k prime. But this is now v dagger s of k I gamma 0 squared, which is minus 1 vs prime of k prime. So this is equal to minus I psi s dagger minus psi s dagger times psi s prime minus psi s prime. And so you see that now, by changing u with v, I changed the second term from psi s to minus psi s. However, the contraction now is with the identity, with 1, which means I still contract psi s with psi s and minus psi s with minus psi s. So overall nothing changes. I get the same minus 2mi delta ss prime. Okay? So unlike the case of the Yukawa potential, where there was no gamma 0 in the middle, and correspondingly I contracted off diagonally. Now there is a gamma 0 in the middle, and then I contract diagonally, and nothing changes by replacing u's with v's, but there's still the minus sign from the exchange of the fermion and anti-fermion line. So that means that overall there's a minus sign and the potential changes. V is now plus E squared over 4 pi r. Okay? And that was to be expected because we know that the Coulomb potential changes sign depending on the charges. So when I have like charges, yeah, it should be minus, sorry. When I have like charges, the charges repel. I have a repulsive potential, but in the case of opposite charges, I have an attractive potential. All right. All right, so now that we can try also to without doing a full calculation, to try to understand what happens when we have a graviton exchange. So I've shown for you what happens with the Yukawa potential when I have the exchange of a scalar of spin 0 particle. Then in here I showed you what happens when I have the exchange of a photon of spin 1 particle. And the next thing one would try to understand would be what happens when I have an exchange of spin 2 particle or graviton. Well, quantum gravity is not well defined non-perturbatively, at least in terms of pure gravity. In string theory it's better. But certainly this is defined perturbatively, so I can certainly write down a Feynman diagram and calculate it. It's just longer. But but on the other hand, we can figure out what happens. So in the case of a vector, the propagator will have indices mu and mu corresponding to the vector indices at each point. And they are contracted in a corresponding Feynman gauge by g mu nu. Now in the case of gravity, I would have a graviton propagator, and then this being a graviton has two indices symmetrized, so it will be mu nu on the left and rho sigma on the right. And then there's a corresponding gauge like the Feynman gauge, because, I mean, roughly speaking, general coordinate invariance is a sort of gauge invariance, in which I can also bring the propagator to the scalar propagator form. So this would be proportional to g mu rho, g mu sigma, symmetrized. Something like this. Now we see what the difference was. So the difference between these two calculations was due to this g mu nu factor, and the g mu nu contracted with gamma mu and gamma nu meant gamma 0 on both sides, and this in turn meant that so there was a sign in g mu nu that came from g00 equal to -1, and then there were signs coming in here, but for particle-particle scattering there was no extra sign. There was just this minus on turning attractive to repulsive, and because there was an odd number of gammas in each u bar u, when going from particles to antiparticles, we get an extra minus sign. So extra minus from gamma zeros, from gamma 0. Now what will happen in this case? In this case, the same logic we use here says that in the non-relativistic limit only mu equal 0 will contribute. So this contribution would be proportional to g00 squared times the scalar propagator. But g00 squared is now +1. Okay? So we don't have this minus sign, so that means we're back to the attractive case, like the scalar. On the other hand, when changing a particle with an antiparticle, the same thing will happen here. Instead of one gamma, we'll have another gamma, right? Because it needs to contract with the same, with the metric indices. But gamma 0 squared is -1. So anyway, the point is proportional to 1. So the change from particle to antiparticle is like the change of particle to antiparticle in the scalar case, where there are no gammas at all. Okay, so there is no change. This is universally attractive. So gravity is indeed universally attractive. So without going into the details, because the details amount to just finding what is the propagator for and the vertex for gravity and all of these things, which are, some details, but you can guess what they're supposed to be. The only relevant thing is, as I said, there are two metrics, and correspondingly they contract with two gammas in the fermion lines. So
this is an analysis in the non-relativistic limit, right?
In the non-relativistic limit, yes.
So it is universally attractive.
Yeah, but that's what we're doing, right? We're calculating the potential, because gravity in the relativistic limit is a complicated thing. It's it's a curved space, which is not easily describable. But in the non-relativistic limit, gravity is described as the universally attractive potential. And that's what we're finding here. All right. So finally now, let's consider the Rutherford scattering. So what is Rutherford scattering? Well, if you remember from history, the Rutherford experiment was the one that defined the fact that electrons move around a nucleus which has positive charge. So at the time of Rutherford, there was this kind of silly idea of an atom as a raisin pudding. Which meant that people thought that the atom was some pudding of positive charge, which had raisins, which were the electrons inside it, right? And you know, if you think of the atom as some ball that you cannot break, then that made some sort of sense, because you know somehow electrons come out of it, and well, that's the simplest thing you can imagine. But then his experiments showed that if you go with an electron through this, you know, it will get a little bit deflected if it passes off center, but not too much. And instead, Rutherford did experiments and showed that there was, I guess like this we should say. There was a strong deflection indicating that the particle was in a fixed, the positive charge was in a fixed point called the nucleus, right? And then around it there were the electrons, but they just screened the charge in the center. But the essential point here was that the charge is viewed as a fixed point, right? And then you send the electron beam and it gets scattered off it. Now, this is a standard example of classical mechanics, scattering in classical mechanics. You calculate d sigma d omega, right? But again, since we're doing this in quantum field theory, we can approximate this with non-relativistic quantum mechanics. And so we consider a non-relativistic quantum mechanics setup, in which case we have what? We have the interaction of a fermion, the electron, with a fixed point. And the fixed point, we understand it as just an external potential. External electromagnetic potential. Okay, so this is the interaction of a fermion with a non-relativistic a fermion with a external electromagnetic potential. So that means that the interaction Hamiltonian psi bar I gamma mu psi interacts with an external, so classical field A mu. right? So then in a scattering, so let's say this momentum P, this is P prime. A scattering element would come from minus I times this interaction Hamiltonian. And we're just contracting these things. I mean, that's the simplest thing we can have, right? So minus I E times the contraction here is U bar of P prime. Then I have I gamma mu. Then this one gives U of P. And then we still have the interaction with the external field, so A mu of x. But remember, we have to put external lines, so we have to put here E I P x, this, and E to the minus I P prime x, for this contraction. All right, so this amounts to, so this is integral v3 x A mu of x E to the I x P minus P prime, which is the Fourier transform of this field. All right. I can cancel this as well. All right. Then, sorry, D3, D4. Because here is the integral over time as well. But on the other hand, we want this electromagnetic field to correspond to a fixed nucleus. So that means it's time independent. So part of this integral, the integral over t. So this is function of x and t, but if it doesn't depend on t, I can do the integral of it e minus e prime. It's just 2 pi delta. Okay, so this is because the source is time independent. And then, since, moreover, as before, the matrix element is Im times 2 pi delta of energy, that means I can cancel this thing. And then for Im, I basically just add, you see, this is a Feynman rule for adding, Feynman rule for interacting with a classical field. So adding this interaction E gamma mu times A mu E minus P prime. Okay. All right. All right, so now let's compute. We're interested in the sigma d omega, the cross section for scattering of the fermion in the case of an A mu coming from a fixed nucleus, right? So A mu coming from a fixed nucleus really means that the potential A0 is plus ZE squared 4 pi r. The potential itself is ZE for 4 pi r. So we want to calculate the sigma d omega in the case of such an A0. And so let's think of a scattering at impact parameter B. So this sigma d omega in the case that the source of the electromagnetic potential is situated at a distance B from the line of the incoming electron. This is the incoming electron and it's situated at a distance B. Then we've noted this already when discussing S matrices. We noted that we're supposed to put this factor e to the IQB inside, e to the IKB inside the wave function for the incoming field. So we'll write some function of k, but then also put this e to the IB square root 2ei. And then the probability, the differential probability of going from initial to final state is proportional to the differential of the final state, d3pf divided by pi cubed times 1 over 2ef from the relativistic normalization. And then the matrix element. Now, in the way we did it for scattering of two particles to two particles. Now, you might want to think of this as some sort of limit of that case, because we're scattering in a case where one particle is classical and fixed, right? That's the nucleus. And only the other particle is moving in quantum. So if you want, you can think of it this way as a limit. And then but in any case, the probability is proportional to the absolute value squared of the transition between the Heisenberg states, the state the initial state with some wave function, and the final state with a momentum Pf. Then the sigma is integral of this, dpIf, but integral over what? Integral over the possible impact parameters. So we're talking about quantum mechanics scattering here, and therefore the impact parameter is a variable. It's not really fixed. And so we have integral d2b, d3pf over 2 pi cubed 2ef. And now we have to write this amplitude and its complex conjugate. But remembering that we have a wave function like this, so from the amplitude itself, we get phi of ki square root 2ei, and then from the complex conjugate, so this is this transition times this complex conjugate. So from the particle itself we get this integral. From the complex conjugate we get integral d3ki bar divided by 2 pi cubed 1 over square root 2 ei bar phi star ki bar, then e to the ib times, from this one we get ki, and for the complex conjugate we get minus ki bar. All right. So this is from the wave functions, but then of course we still have the amplitude to go from a state of given momentum k to a state of given momentum p. So this would be out pf ki in times the complex conjugate. Out pf k bar I in complex conjugate. All right. So this is the integral we have to do. This is all very similar to what we did for the 2 to 2 scattering, because as I said, you can really think of it as a limit of the 2 to 2 scattering. Then we just remember that this matrix element is Im times 2 pi delta of energy, and complex conjugate is minus Im minus Im star initial going to final 2 pi delta E final minus E bar I. Then what? We can do the integral over B. So integral d to b e to the ib ki minus ki bar is 2 pi squared delta to ki perpendicular minus ki bar perpendicular. Perpendicular means spatial and perpendicular to the direction z of motion. And then so these are the objects that appear in the integral. But then we have these two delta functions that we're generating. And the energy is related to the momentum in the propagation direction, that's called z. So E squared is equal to kz squared plus m squared, right? So I rewrite this as the second one as delta of well, I guess I should say perhaps let me write this. So this is a product of two delta functions, but one element is the same, ZF. But that means that I can rewrite this as delta of EF minus EI times delta of, and here I replace EF with EI minus EI bar. And then this one, I can think of it using this relation as delta of Ki Z minus Ki bar Z divided by dE dE dk. But then I have that E dE from this is equal to Kz dkz. So that means that dE dkz is equal to Kz over E. So this is equal to Kiz over E. And further, then I have this delta function, but then I also consider the integration over Pf. So if I use this integration over Pf, 2 pi f, 2 pi third to 2ef times delta function of Ef minus Ei, this is equal to, so here this is Pf squared dPf d omega. D omega is what we want to divide by at the end, the cross section, d sigma d omega. And then dPf, Pf squared, 2 pi cubed 2Ef. And I rewrite this as by the same kind of relation, so delta of Pf minus Pi divided by Pf over Ef. All right, and we see that one Pf cancels with one Pf and Ef with Ef. So this is d omega over 4 pi squared, or 8 pi squared, sorry. Then doing the integral over pf, I'm left with pi. Well, no, perhaps I can still write it as, just leave it like this, because this still acts on stuff. So dpf, pf, delta pf minus pi. All right. So now, we have what? So we have that the sigma is equal to, we've taken care of these two integrals, taking care of this and of this, right? Yeah. And finally, considering the case where, as before, the wave function is almost a delta function. Wave function being a delta function means the probability is equal to the delta function, and probability is phi star phi. So phi of k, absolute value squared, is 2 pi, say 2 pi cubed, delta 3 k. Well, so these are the actual initial momenta. So ki and k bar I are integrated over, but in the wave function, but then the wave function is considered to be centered or on initial momenta pi. Okay, and all right. So all right, so let's consider all the factors that we obtain. So we obtain a delta function in ki z minus k bar I z. We obtain this other delta function in ki perpendicular, ki perpendicular, and yeah, so that's it. So this is these are all the delta functions that remain. So that allows us to get rid of this integral, because here this is equal to d2 k bar I perpendicular dki bar z. Okay, so when we do these two integrals, then we get rid of the delta functions equating k with k bar. All right. So then this thing, this denominator becomes the same. So square root 2ei together with this. And so let's see what we're left with. So let me write an intermediate step now. So we have gotten rid of all the things that I circled, and we're left with integral d3ki over 2 pi cubed. And here, square root 2ei times square root 2ei, so 2ei. Then ki bar is now equal to ki, which means I form this absolute value of phi ki squared, which is 2 pi cubed delta 3. 2 pi cubed delta 3 of k minus pi. So that takes care of this as well, and I'll put the k's with equal to pi's. Then I get, well, m squared. I still have this 2 pi squared. I have from here 1 over kiz divided by e, so e divided by kiz. Then I have the omega, which I can put outside. And 1 over 8 pi squared and dpf pf delta pf minus pi dpf pf delta pf minus pi. All right. Oh, this was EI, right? Yeah. EI cancels. Okay. So 4 pi squared divided by 16 pi squared. Oh. I think I lost some pi somewhere. These pi's were somehow canceling something, I'm not sure where.
When you've done this integral over d3k bar, you had only canceled 2 pi squared, right? There is 1 factor of 2 pi in the denominator.
Oh, okay, good.
But there is still 1 factor of 2 pi.
There's still 1 factor, yeah.
I don't know.
So I cancel this with this, and I'm left with. So yeah, maybe let me put it here just. Yeah. Okay, and 2 pi delta AF minus EI, delta AF minus EI. Oh, yeah, I forgot it here. I just, it's not 8 pi squared. It's 2 pi cubed times 2, so that's 16 pi cubed. All right, that's good. Squared. And so finally I get then that d sigma d omega is equal to integral dpf pf delta pf minus pi and I going to f squared divided by 16 pi squared. And then KIZ, but the momentum is, divided by the energy is by definition the velocity. This is in the direction z, which is the direction of the momentum. So KIZ is VI E. EI. Okay. So that's the formula that I wanted. But now I have to substitute. I have to substitute what I had written before for the amplitude. So I had written that Im was equal to E U bar Bf gamma mu Pi times A mu of Pf minus Pi. And this one itself, we've said that was equal to, well, A0, and then delta mu 0 times Ze over 4 pi. So A mu A0 of x was equal to Ze over 4 pi r, which means that in momentum space A0 of p, we did that already, so this is just Ze over q squared. Right? We did this. Actually, what we did, to be honest, we did it for the Yukawa, and then we took the limit and go to 0. So that's how you actually do the Fourier transform. You have to introduce this, regulate the mass, and then take the mass to 0. So now A0 of p is equal to Ze over q squared, in this case Pf minus Pi squared. So that's the matrix element.
Sorry, why do you have only the 0 component of 3?
It's a static source, right? The static source is just E0. And then, so that means that, m squared, first of all, I need to calculate the square of this thing, so and as you see, I have delta mu 0, so gamma 0 Pi. And then this thing, as we saw, this was equal to U dagger S times I times minus 1 UR, and this is equal to, this is still times delta Pf minus Pi. So this is psi dagger S, psi dagger S times I1 times psi R. So this is times 2m. So this is 2m times m, sorry. This is 2m delta Rs. Okay. So then I have this factor minus I, but in absolute value squared that cancels. So this is absolute value of 2m delta Rs. So that's, and well, sum over the final spin. So sum over S. The final spin is unknown in this case. So this gives just 1. The delta G gives just 1, and then this is 4m squared. Okay? That means that matrix element squared is equal to, well, I have this E squared, then this matrix element squared, which is 4m squared. Delta mu 0 is implicit, I already took that. And then ZE squared over PF minus PI to the 4th. All right. So finally, that means that d sigma d omega is equal to integral dpf pf delta pf minus pi 16 pi squared vi pi, and the matrix element squared, which is z squared e to the 4 times 4m m squared divided by pf minus pi to the 4. So now let's consider a bit of geometry. So the initial momentum, let's call it pi, and the final pf, and then the angle between them will be called theta, and then this is theta over 2. And of course, momentum conservation means that, energy conservation really is that Pf is equal to Pi in absolute value. So, so from this, we see that this object, which is Pf minus Pi, so Pf minus Pi is equal to what? Is equal to twice this, and this is pi times sin theta over 2 pi sine theta over 2. And further, we are in the non-relativistic case. So pi in general is VIE. But in the non-relativistic case, is VIM. Right? So 2m VI sine theta over 2. So it means that d sigma d omega this, as I said, gives us. So I kept Pf minus Pi in order to remember that in this one I have absolute value Pf equal absolute value Pi. But now I can do this integral, is just Pi. So Pi, which is approximately equal to MVI over 16 pi squared vi ti. And ei is approximately equal to m. So these things cancel. Then z squared e to the 4 m squared over this thing to the 4th. So yeah, 2m to the 4th vi 4 sine 4 theta over 2. This reduces to the second power, and we get z squared e to the 4 over 16 pi squared. Well, 16 times 4 is 64. Pi squared m squared vi 4 sine 4 theta over 2. No, I've did something wrong with the pi's and 2's. What did I do wrong? No. Wait. Oh, sorry. No, I didn't do anything wrong. Yeah. I just rewrote this in a different form. So now I remember that E squared of 4 pi is called alpha. This is the electromagnetic coupling that is about 1 over 137. So this is written as z squared. So I take 16 pi squared from this. I'm left with 1 over 4. So z squared alpha squared over 4 m squared vi 4 sine 4 theta over 2. Yeah. All right. Yeah. So this is indeed the formula found by Rutherford. And as I said, this formula was originally found from a classical calculation. This is just a standard application of scattering in classical mechanics. But here we found it from quantum field theory in the limit first of quantum mechanics. We only looked at tree scattering, and second, non-relativistic. Okay, so non-relativistic quantum mechanics gives us the same as the classical scattering found by Rutherford. All right, so that's everything I wanted to tell you today. Do you have any questions? All right. Then let's finish here. Sorry, I only had time to correct one set of homeworks from homework 19. The other ones I haven't finished yet. I mean, almost everybody did everything correctly. The only unknown was it wasn't very clear in the statement of the problem, I suppose. So some of you noted that. So one exercise was to calculate decay of a particle into two scalar fields phi, and the lifetime for the decay. And some of you noted that the two phi's were identical. So then indeed one has to put a factor of 1/2. But I mean, the way the problem was stated was not completely clear. Most of you, I guess, thought that the particles could be differentiated, and in principle it could be that this is the case, so I gave full marks for both ideas. Otherwise, I think everybody did correctly. I mean, some of you did some like algebraic errors or something, but ideas were there. I don't know. Do you have any questions about this Arnold for 19? Sketching?
Not to mix.
Oh.